Good evening, friends. Let's take a look at the first two or three special cases of this modular arithmetic result. So n equals 0, if you substitute right here, you would get 4 on the left-hand side. And notice that is not congruent to 2. And again, we're talking modulo 8 down here. Okay, now by n, I mean positive integers, right? Some people include 0 in here. Now, but I just showed you that that's why we're just doing positive, okay? Because it clearly doesn't work for the case n equals 0. Now let's do n equals 1. When you do n equals 1 right here, folks, you get 3 squared plus 1, which is 10, which is certainly congruent to 2 mod 8. And again, I'm leaving this out. 10 minus 2 is physically 8. Okay, let's try out n equals 2. So this would be 3 to the 4th power. 2 squared is 4. 3 to the 4th is 81 plus 1. So this would give 82 is congruent to 2. Okay. So we do, because again, the difference between these two numbers is a multiple of 8, namely 10 times 8. Okay. So it does work for cases n equals 1, n equals 2, okay? Let's try to prove it for all, okay? So now, y'all, this involves what I call kind of some not so natural laws of exponents. If we take a look at this result right here, it's important to get the 3 out, and it's kind of hard to motivate that until you think about the binomial theorem. Okay, but anyway, notice that this result here works out just fine because you're actually adding exponents. You got an exponent applied to an exponent, which is kind of confusing. Okay, but you see you have this right here. You have the same base. So you see what you end up with when you add the exponents is 1 plus n minus 1, right? And that's kind of neat. And it's when it starts getting into these tower power sort of thing, it can be kind of confusing, or at least for me. All right, but you see that adds up to just the n that you see right there, which is the object we're interested in, okay, and when you add 1 to it, okay? So this turns out to be quite useful because this piece right here is just 9, right? It's 9 raised to this power, okay? So let's keep going. Now the approach I'm going to use is the binomial expansion. You could do it modular arithmetic, I'm sure, but it was kind of neat how this, the binomial worked out very nicely. You just wrote 9 is 8 plus 1. You see, this is exactly what we have here, okay? Is equal to this object, all right? And we do 8 plus 1. 1's always a nice term to have in the binomial expansion because everything, just all the powers of 1 are just 1, okay? Now I'm putting the 1 here just to keep things straight. So y'all, this is the binomial expansion if you recognize it. The first term is always just the power that you see right here, or the number that you see right here. And the last term would be 1 raised to that very same power. You can see right here how, and if you guys work with simpler cases, this is always true. You start and end with the same power applied to the different elements in the binomial, okay? So what do we got? Yeah, right here and right here. So that's kind of a reality check that you're doing the binomial right. Now, these are the binomial coefficients. It's a little hard to get used to this, but if you think of this as just n, remember this is n, choose r here. And you got this relationship with this part, this part, this part, this part. It's a little hard to keep up with when you have these power type exponents of exponents sort of thing going on. Okay. Now, what is crucial to notice right here is that really I could have gotten by without writing the binomial coefficient, right? Because you can see you have a power of 8 everywhere except at the very end here. So, and remember, we are trying to show, and y'all, by the way, just to make sure I'm making a little bit of sense here, this is the same thing as saying 3 to the 2 to the n plus 1 is equal to 2 plus some multiple of 8. We'll just call it k. Have we used k yet? It's equivalent. This statement and this statement are absolutely equivalent, okay? Now, so, right, it's manifest, right? what I'm going to do is I'll circle this piece right here. Circle this object that is part of the binomial expansion. Okay. All right, so this is clearly, you got 8 here, all the way to the end until you get to 1 raised to the, this is just 1, right? And I did the red here. I thought that was kind of useful, right? So this is equal to 8k plus 2. And we can say QED. See, this piece 8k corresponds to the circled piece up here, and then you got the 2 1s here to make it work out nicely. And also, this also actually proves that 2 divides the expression exactly, because you can factor a 2 out of here. I should just do another video. Why not? But this is 4k plus 1, right? So this also proves that 2 divides our expression exactly, since this is an odd number. No higher power of just 2. There's no higher power of 2 that divides our expression. Okay, that's written as what do we got here? What's the problem? Okay, 3 to the 2 to the n. That's another way of saying that 2. The notation, folks, that we use here would be 2 double vertical bar, 3 to the 2n. Plus 1. And this means it divides exactly. Okay, again, it's big. No matter how big gets, you're never going to have a multiple of 4, multiple of 8. This is the highest power of 2 that divides this thing. Okay, so that's a consequence of just writing it this way. Okay, so I think that's it. And well, I don't know if I can do any computations. What if this were 3? This would be 3 to the 8th. I don't know about that number. It's too large for me to calculate. But in any event, we have proven it down here without much doubt. And oh yeah, by the way, folks, I'm sure you noticed I didn't go to the trouble. There's powers of 1. You know, I'll write 1 to the m is equal to 1, right? See, technically, I should have written that down probably. This would be 1 to some power right here, 1 to some power right here. It'd be 1 to the first, I guess, 1 to the second, all the way out. I just left that out, okay? But this is a correct. I double checked this at the binomial expansion computation. And so we finished the problem. So thank you for viewing.